Imagine you're faced with the problem of computing an integer number represented by an unsigned in down a tree, where each node's value is calculated recursively by multiplying its children's values. The issue at hand is frequent overflows during these calculations. However, in this case, you're not concerned with the exact value of the result as long as it's greater than a certain threshold. Let's call it some big value. An approach to handle this involves using a convention where the value 0 signifies any high number that exceeds some big value. The proposed solution aims to address this concern by setting up a mechanism to detect and handle potential overflows. Now, let's delve into the solution provided. The first part involves defining some big value as the square root of UINT MAX, which helps prevent unsigned overflows when multiplying two numbers. This definition is set up in a way that ensures the calculation of some big value occurs only once, thus optimizing the process and enhancing efficiency. Additionally, a runtime check is included to compare A and B with big value to spot any potential overflow scenarios. Moving forward with the solution, another approach is introduced using the bit width of the unsigned data type to determine some big value. By calculating some big value based on the bit width of unsigned, the risk of overflows can be mitigated more efficiently. This method offers a structured way to handle potential overflow situations, providing a more robust solution to the problem at hand. Expanding on the solution further, a detailed mechanism is presented to determine the number of value bits in UINT MAX, considering the possibility of padded types. This approach ensures that some big value is accurately defined, taking into account variations in the representation of unsigned across different implementations. By incorporating this level of precision, the solution offers a reliable way to manage and prevent overflows during the integer calculations down the tree. Continuing with the solution, a runtime check is suggested to assess the likelihood of an overflow occurrence when performing the multiplication operation. By dynamically evaluating the values of A and B, this check adds an extra layer of protection against potential overflows, enhancing the overall robustness of the calculation process. Lastly, a more comprehensive approach is outlined, utilizing a wider data type for the multiplication operation to avoid unsigned overflows. By considering the use of unsigned long for the product of A and B, the solution offers a higher capacity to handle larger results without encountering overflows. This step provides an added level of security and reliability in the computational process, ensuring the integrity of the calculations performed. In summary, the solution provides a multifaceted approach to tackling the issue of unsigned overflows during integer calculations down a tree. By implementing a combination of predefined thresholds, bit width considerations, runtime checks, and wider data types, the solution offers a comprehensive strategy to manage and prevent overflows effectively. Remember, when dealing with numbers, it's always better to be safe than sorry. So, until next time, stay curious and keep coding. Don't forget to like, subscribe, and comment below with your thoughts. Who knows, your comment might just be the next big thing in the world of programming jokes.